Morning, guys. Our next lesson in the probability unit is called mutually exclusive events. Now, normally when I do this lesson, I survey the class to help us answer some of the questions. I'll ask how many people went to St. Kevin's, how many people have blonde hair, how many people have blue eyes. Now, since we don't have that, what I'm going to do is I'm just going to write some preliminary information so we can answer our questions. So in our class today, we'll do a pretend scenario. We've got 15 girls and 10 boys, 25 total kids. I'm just surveying the class. I'm just pretending, okay? For eye color, pretend survey again. Brown-eyed kids 9, green-eyed kids 7, blue 6, hazel 3. Just write that down for me. Hair color, 18 brown-haired kids, 7 blondes. Remember, we're adding up to 25. Let's double check this. 10 and 15, yep, 25. And then just write down one other small little fact, that we have 3 blonde-haired students with blue eyes. Okay, and again, the reason why we're writing down this silly information is if we would have been together in the classroom, I would have surveyed and found how many people have brown eyes, how many people have green eyes, how many people have brown hair, blonde hair. But because we can't survey, I'm just pretending. We're making this up. Okay, let's start. Silly little example. Today we're going to look at eye color, green or brown. What is the probability of randomly selecting a student in our class that has green eyes? So again, our normal procedure with a probability is to write down what we're looking for, write down our blank fraction. Our bottom of our blank fraction represents the total number of people that we're pretending to have, 25. And the top number is our desired, and that's how many of the 25 have green eyes. And we pretended 7. So my probability of green is 7 out of 25. Okay. What is the probability of randomly selecting a student from our class that has brown eyes? Again, blank fraction. Bottom part of the fraction always done first, the total. Desired is we're looking for brown-eyed children, 9 out of the 25. Okay, let's keep going. What is the probability of randomly selecting a student in our class that has green eyes and brown eyes? Does that even make sense? Does that mean a person with one green eye and one brown eye? This is the and. This is the intersection. This is the overlap. Now, again, bottom number is 25. And I guess even though it is possible, what do you think the likelihood is that you're going to meet somebody who has one brown eye and one green eye? So in this particular case, there is no overlap because the and is basically impossible. It could happen, but it's pretty likely that it's impossible. What is the probability of randomly selecting a student in our class that has green eyes or brown eyes. So this is the OR, this is the union of sets. Well, we know from the past that we can do the OR two ways. Visually, and the visual technique says add numbers in circles. No, I don't necessarily have something drawn, but let me draw something. I'm going to draw a green circle, and I'm going to draw a brown circle. I'm going to represent them in a rectangle. Green-eyed children we said were 7. Brown-eyed children we said were 9. And we said that we had 25 kids in the class. So that means the entire set should add up to 25. And these 9 people over here are my non-green-eyed, non-brown-eyed people. They're my blue and my hazel. Okay. So if I'm going to add the numbers in the circle, I'm going to add 7 plus 9. And that's going to give me 16 out of the 25 have brown or green eyes. Now, I can also look at it by formula. And if I look at it by formula, it's going to be the probability of brown or green is the probability of brown. That was 9 out of 25. Plus the probability of green, which was 7 out of 25. Minus, there's no overlap here. There's no overlap. So notice I'm not even going to have to minus anything. There's absolutely no overlap. 16 out of 25. Both techniques are giving me 16 out of 25 for the probability of a green or brown-eyed individual. Visual technique, add the numbers in the circle, the 7 and the 9. Formula technique, add all my browns to all my greens, no overlap. Now, the important thing to note is that when there is no overlap, the sets are said to be disjointed and therefore mutually exclusive events. So what we just discovered is that when there is no overlap, the sets are disjointed. Let's highlight that. And you can see that. And they're considered mutually exclusive events. Okay. Kind of cool. We've seen this before. We've seen the OR before. The only thing that we haven't really said is we haven't given them an official name as mutually exclusive events. I've talked to you a little bit about disjointed. We've done, examples where the circle, there's no overlap. So we've seen this before. The only thing that we haven't addressed is the fact of, hey, these are mutually exclusive events. Okay. Let's look at another silly example. I'm going to keep the preliminary survey data just there so we can reference it, okay? Here comes our second silly example. Let's look at 2 other features, blonde hair and blue eyes. What is the probability of randomly selecting a student in our class, that's our 25 people, that has blonde hair? Our pretend example, 7. What is the probability of selecting a student from our class that has blue eyes? Again, 25 kids in our class. we said our blue-eyed children were 6. What is the probability of randomly selecting in our class and getting a blonde hair, blue-eyed child? Now, this is possible. This is possible. It's not like the green eye, brown eye, where I don't think I've ever met anybody in my life who has 2 different colored eyes. You might, but unlikely. But I can honestly say, how many blonde hair, blue-eyed people have you seen in your life? So according to our stats, out of the 25, they were blonde and blue. So again, this is the intersection. This is the overlap. This is the and. What is the probability of randomly selecting a student in your class that's blonde or blue? Well, again, this is the or, this is the union, and the probability of blonde or blue, 2 techniques, visual technique, which is add numbers in circle. And I know we don't have any circles, but we're going to get some here. Here's my blonde. Here's my blue, putting them in a beautiful set. Notice I'm overlapping them this time because there were 3 people, according to our pretend survey, that had blonde hair and blue eyes. Now, let's cover up and look at the blonde circle. According to my data, there should have been 7 blondes. 3 of them are already accounted for. According to my data, there should have been 6 blue-eyed children. 3 are accounted for. So when I add the numbers in the circle, I'm getting 4 and 3 is 10, and another 3 is 13, but I had 25 people in the class. So that means 12 people are non-blonde and non-blue-eyed. Now, if I had to answer the question, what's the probability of being a blonde or a blue, and I added up the numbers in the circle, 4 plus 3 plus 3 over 25, 10 over 25, 2 over 5 is my probability of that occurring. Now, according to the formula, if I use the formula, it would be probability of blonde or blue equals the probability of blonde. Now, that was 7 out of 25. Plus the probability of blue. That was 6 over 25. Minus the probability of blonde and blue. And that was 3 out of 25. So, probability of blonde, 7 out of 25. Probability of being blue-eyed, 6 out of 25. Probability of being blonde and blue, the overlap. And that gives us, again, a beautiful 13 minus 3, 10 out of 25. 2 over 5. Now, remember, let's reiterate. When you are using the formula, you are not looking at the picture at all. You are looking at our given information. When you are doing the visual technique, you're really doing everything from the picture. You're sort of jumping back to the given information, but you're not exclusively relying on it completely. Now, let's talk. It says if there's an overlap, which there is, the sets are said to be jointed and non-mutually exclusive events. Mutually and non-mutually exclusive events refers to meeting two criteria. So think about the criteria in the first example was eye color. And in the second example, there was two criteria, not one criteria. In the first example, one criteria. Everybody was looking at eye color. In the second example, the criteria were hair color and eye color. This is what changes things. Okay, not that I'm ever going to ask you, what are the criteria? Is this mutually exclusive? Is it not mutually exclusive? No, I'm not going to ask you any sort of definitions, but you need to understand the different type of events. These type of events, being a blonde and blue-eyed person, it's likely and it's extremely common. Versus having brown and green eyes, I mean, sure, could you meet a person with a brown eye and a green eye? Yes, but it's very unlikely. This is everyday norm. Okay, let's keep going. I don't think I need our preliminary information anymore. I think we can move on to what I will call more test-worthy examples. I mean, I'm not going to give you a question on the test about people's eye color and this type of stuff, right? Okay. You roll a single die. Okay, so you can envision it. Little single die. What is the probability of rolling a 3 or a 5? Now, I don't think I'm going to draw the picture here. To me, this is a beautiful Formula 1. Probability of rolling a 3, 1 out of 6. Probability of rolling a 5, 1 out of 6. Minus the probability of throwing a die and having it turn up 3 and 5 at the same time. Absolutely can't happen. Mutually exclusive event. It can't happen. You're not going to roll the die and see 3 turned up and see 5 turned up at the same time. So 1 over 6 plus 1 over 6 is 2 over 6, or 1/3. This is referring to at the same time. Okay, you roll a single die. What is the probability that it's either going to come up even or greater than 3? Different scenario. This is the blonde, blue-eyed child. Well, what's the probability of rolling a die and it being even? 2 is even, 4 is even, 6 is even. What's the probability of being greater than 3? A 4 is greater than 3, a 5 is greater than 3, a 6 is greater than 3. Minus the probability of being even and greater than 3. So, hold on, we said greater than 3 was the 4, the 5, and the 6. Greater than 3, those are all my greater than 3 numbers. Now, which of those are even? Meeting both, meeting both criteria. Even, out of the 6, they're even and they're greater than 3. 4 is an even number greater than 3. 6 is an even number greater than 3 out of all the 6 die. So 3 plus 3 is 6 minus 2, 4 out of 6, 2/3. The probability of having an even roll greater than 3 is 67%. Again, mutually exclusive, non-mutually exclusive. This is possible and quite likely, 67%. Completely 100% impossible. Okay, a card is randomly drawn from a deck. Got it? What is the probability that the card is a face card or a spade? A face card or a spade? So hold on, let's start with probability of a face card. Out of 52, jacks are face cards, queens are face cards, kings. Jack, queens, kings. Probability of a spade, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And, sorry, what's the probability of being a face card and a spade? How many face cards are spades? Jack of spades, queen of spades, king of spades, face cards, and spades. So 12 and 13 is 25 minus 3. 22 out of 52, 11 out of 26. Probability of picking a face card, that's a spade. So notice some of our OR questions definitely lead themselves to the formula. Okay, in a recent survey of university students, 85% consume alcohol at least once a week, 35% smoke at least occasionally, and 25% do both. Ding, 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 ding. Overlap. Overlap. So what is the probability that a university student is chosen at random that smokes or drinks? I think this one leads itself to a picture. I mean, we could do it, but I think it leads itself to a picture. Let's do drinks. Let's do smokes. Beautiful rectangle. Now, they said 25% do both. 85 drink, but 25's accounted for. 35 smoke. 35 smoke, but 25's accounted for. And hold on, in the entire set, we've always got to think about this, right? 60, 85, 95. 5% are my non-smokers, non-drinkers. So when I have a picture and I'm doing the OR, I add the numbers in the circles. 60%, 25%, 10%, 95% chance of meeting ourselves a drinker or a smoker. Beautiful. Remember, this number is super important. You do not move on to the probability, answering the probability until all of the numbers, circles, and outside are filled in. Okay, now, our very last example, can you do me a favor? And can you put a whole bunch of stars? You're guaranteed to get a dice chart question on the test. Okay, now let me explain how the dice chart questions work. Basically, what happens in a dice chart question is that I pretend that I'm holding a die in my hand. Another student pretends that he or she is holding a die in their hand. And we both throw the die on the table at the same time. And when the dice stop rolling, my partner and I, the person I'm playing the game with, we add up, we sum up, we total up the two dice. So if I roll a 1 and my partner rolls a 1, snake eyes, the total is 2. If I roll a 1 and my partner rolls a 2, the total or sum is 3. If I roll a 1 and my partner rolls a 3, the sum is. If I roll a 1 and my partner rolls a 4. If I roll a 1 and my partner rolls a 5. And if I roll a 1 and my partner rolls a 6. This chart has to be memorized by you. It will not be given on the test. It will not be given very often. You got to write it down. Okay, let me keep going. I get a 2 and my partner gets a 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So the idea is if I roll a 1 and my partner rolls a 1, the total is 2. If I roll a 6 and my partner rolls a 6, the sum or the total is 12. Now, when I look at this, if I count how many possibilities there are, 1, 2, 3, 4, 5, 6, and there's 6 rows, my NS, my total options, is always going to be 36. So that's kind of helpful. It's kind of really helpful with the dice chart. Again, you have to memorize how to draw this chart. It's not going to be given to you. Okay, let's look at part A. What is the probability of rolling a sum or a total of 10? Well, I know that my NS is 36. And out of the 36 options, how many of them are 10s? 1, 2, 3. Now, let's think about what those options are. 6. Sorry, guys. 6, 4. 5, 5. And 4, 6. That makes sense. 4, 6, 6, 4, 5, 5. 1 out of 12. Those are my options for a sum of 10. What is the probability of rolling a total of 4 or less? Again, 36, a total of 4. 1, 2, 3, or less. 5, 6. No, let me do that again. 1, 2, 3, 4, 5, 6. 6 out of 36. Again, a total of 4, 3, 1, 2, 2, 1, 3, or less than 4, 2, 1, 1, 2, 1, 1. 6 out of 36. What is the probability of a total of 10 or a total of 4 or less? A total of 10 or a total of 4 or less. Again, we've got 2 ways of doing this, right? We have our visual way. Now, I don't have circles. I have the dice chart. And I've got my formula technique. Let's attack it with the formula technique first, guys. Let's attack it with the formula technique first. And then we'll do it with the visual. So probability of a total of 10, we already calculated, was 3 out of 36. Probability of a 4 or less, we already calculated, was 6 out of 36. Minus the probability of a 10 or 4 or less, that's a mutually exclusive event. That can't happen. I can't roll the dice and have a total of 10 or have the total of a 4 or less. 9 out of 36. 1/4. Okay, so can we go up to the visual for a second? I want all the totals of 10s. There they are. I want all the totals of 4 or less. There they are. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 36, 1 out of 4, and that's my yellow highlight. Again, visual ways still exist for OR. The only difference is the visual is not the Venn diagram, but the dice chart. Okay, let's keep going. What is the probability of rolling a total of 10 or a 4 comes up on one of the dies? Now, not a total. A 4 comes up rolled on one of the dies. Okay, again, visual. And formula. Let's attack it from the formula first. Probability of a total of 10. We've already calculated that. 3 out of 36. Probability of a 4 on one die. Let's scoot up to the picture for a second. Let me get a different highlighter too. A 4 on one of the dies. So watch me for a second. Here's the option of 4, 1, 4, 2, 4, 3, 4, 4. We'll talk about it in a second. 4, 5, and 4, 6. That's a 4 on this die, some other number on the other die. Now, a 4 on this die, 1 on the other, 4 on this die, 4 on this die, a 4 on this die, and a 4 on this die, and a 4 on this die. So let us add up all of those orange options. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 out of 36 has a 4 on one of the dies. Now, I know this is going to cause some people a little bit of grief because the argument is that I rolled a 4 and my partner rolled a 4, so that's a 4 on both dies. But really the question is on one or the other, and it is. You could look at it as the 4s on my die, or you could, and it's not counted twice either, or the 4s on my partner's die. It is for my black and white people. Some of you are going to have to just deal with that. It is one of those issues that, we could get into, debating over, but it isn't. It's 11 out of 36, a 4 on one of the dies. Now, let's subtract the and let's look at our chart here for a second. And I want you to look at your chart and I want you to see where we have a 4 on the die, one of the dies, but the total of the two dies is 10. A 4 on one of the dies, but the total is 10. A 4 on one of the dies, but the total is 10. So 3 plus 11 is 14, minus 2, 12 out of 36, 1/3 opportunity. Now, let's take a look at visual technique. Visual technique, I'm going to highlight in pink anything that's a total of 10. I'm going to try to make it really hot pink there for you. or anything that's got a 4 on one of the dies. So look to my area that's pinky orangey. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 36, 1/3. Now, some of you are going to look at this and say, Ms. Martel, why would I ever use the formula when I can do these visually, and visually just means that I'm going to count? And it seems so much easier to get the highlighter out. I understand, and I totally agree. Part of the problem is that these questions are always worth 2 marks. So let's say that you choose visual technique and you write down 11 here. You're losing 1.5 marks because I have nothing to follow your logic. But if you choose this technique and you got this right and you got this right and the setup is right, but this is wrong, you'll lose 1/2 mark. So again, this is all about maintaining marks and strategy, right? So I'm not in disagreement. I always use the formula first, check with my visual. That's my technique, because I don't want to lose 2 marks just because I counted wrong. And it can happen. It happens to all of us, right? Okay, let's look at our last example. What is the probability of rolling a total of 10, and a 4 on one die? Oh, okay. The and situation. A total of 10. A total of 10. I know that that's 36. Let me go up to the visual. God, I'm running out of colors and I don't even know. A total of 10. And a 4 on the die. Well, this one is 4, 6. This one is 6, 4. That's a total of 10, but it's 5, 5. So a total of 10 that has a 4 on the die, or on one of the dies, 2 out of 36. These are going to take some practice. They're either going to be a real easy way to get 10 marks or a real easy way to lose marks. So when you see a dice chart question, please make sure that you're practicing it. Thank you.